Hello Chem class. Today we're going to be working with half-life problems, and in specific in this video we're going to be covering fractions of material left, and we're going to focus on carbon-14 problems with this as well, although this should be relatively similar for any isotope. So let's get started. What fraction of carbon-14 will remain after 3 half-lives? For this we're going to have to set up our table. Here we have the start of our table, and these two columns are always going to be the same no matter what problem you're doing, so that makes things at least a little bit easy to start with. So we're going to plug in our number of half-lives, and it's very important when you do these problems that you start at time 0, and so your number of half-lives is actually going to be 0, which means you have the whole sample left, so we could write 1 over 1 if we wanted to there. After we go through 1 half-life, by definition that means that we should have a fraction of 1/2 of our material left. When we go through a second half-life, we should be at 1/4 or half of half. And when we get to the third half-life, we are down to 1/8. So when you're doing the fraction left column, you are always dividing by 2 in order to get your fraction left. At this point we can answer the question because it says what will remain after 3 half-lives. Well, we can see that our at 3 half-lives here we have 1/8 left. So the answer to this first question here would be simply 1/8. If we change our question to say what fraction of carbon-14 will remain after 22,800 years, it's still handy to have these first two columns for your chart, but now we're going to have to add another part to this. Our new column here is age, and that's always going to have a time unit. This is a column that will vary depending on what the material is that you're dealing with. The unit could be seconds, it could be hours, minutes, years. In this case, we're going to be dealing with years, and carbon-14 value we said is 5,700 years for a half-life. Note that what I'm going to do here, though, is at 0 time, I'm actually going to be putting in a 0 for the age. Don't make the mistake of putting the 5,700 first. The 5,700 years doesn't happen for carbon-14 until the first half-life. At this point, for age, we are going to be adding 5,700 each time. This is different than the divided by part that we did on divided by 2, so please don't multiply by 2 or divide by 2 in this column. It's adding 5,700 every time. So when we go through a second half-life here, we are going to be going up to an age of 11,400 years. And then when we get to 3 half-lives, we're going to add 5,700 yet again, and that gets us to 17,000. There we go. And we are trying to get to 22,800 years, and we're not quite there yet. So we're going to have to add a 4th row to this thing. So we're going to say number of half-lives 4. We're going to divide by 2 again. That's going to give us 1/16. And now when we add 5,700 to our 17,100, we get 22,800 years. So what this is telling us here is that the answer to our question is going to be 1/16. That's the fraction left after 22,800 years. Okay, so those are some questions dealing with the fraction. I'll try to do some more videos with some other carbon-14 problems and post them as a separate video. Over and out. 100, whoops. Hello, Chem class. I have another carbon-14 problem for you, and this time we're going to be figuring out the age of 3 grams of this woolly mammoth hair. It was found in Siberia, and it is emitting 2.8 decays of carbon-14 per minute. I have here given you two of the values that you will be receiving on all quizzes and tests, so you do not have to memorize them, the half-life of carbon-14 and the carbon-14 living decay rate. So let's get started. The first thing I've done here is to set up part of the table that I might use to solve the problem. I really don't need the first two columns of n, or number of half-lives, and the fraction left, but I'm going to put them in the problem anyway, just so you can kind of see how these problems might end up working. The very first thing that I notice here is that my unit here that I'm working with is going to be in decays per minute per gram, but when I look at my problem, I will notice that the decays per minute is given and a separate gram value is given, and this can be the case sometimes. If those are separated, you first need to put those two together to get the full unit of decays per minute per gram. So let's go ahead and do that. Off on the right here, I've now taken my 2.88 decays per minute and I've divided it by the 3 grams so that I can get the appropriate unit. When I solve this in my calculator, I end up getting 0.96 decays per minute per gram, and so this is the value that I'm really going to be looking for as I set up my table under this column in order to figure out the age. Let's go ahead now and start filling out the columns. So we're always going to start with the first two columns being the same as any other problem. So I'm going to begin with times 0 half-lives. Fraction left will be 1 out of 1. We're starting with our original sample, and according to our half-life here of 5,700 years, we're going to have to put that in here, but we don't want to put that 5,700 years here for the first age. Instead, what we would like to do is start with an age of 0, because no time has passed, and that means that our decay rate is for a living organism, since no time has passed or it just died, it would be 15.3 decays per minute per gram. So we're going to go ahead and put 15.3 in there. Okay, next we're going to make the next row. So after 1 half-life, we're going to be down to 1/2 of our original carbon-14, and now that means we get to put in the half-life, 5,700 years. And the decay rate here is going to end up dividing by 2, so we're going to end up with 7.65. We're not to 0.96 yet, so we're going to have to keep going. So we go through a second half-life. That brings us to 1/4, which is 11,400 years. And 7.65 will be cut in half yet again to 3.83. We're still not to 0.96 rather, so we're going to go through a third half-life. That's going to be 1/8 half of what we had before. We're going to add another 5,700 years to our time here, so that will end up being 17,100 years. And our decays per minute per gram are going to be cut in half yet again, and that comes down to about 1.91. We're still not at 0.96 decays per minute per gram, so we're going to do this one more time. Fourth half-life brings us to 1/16 of what we originally started with. We're going to add yet another 5,700 years. That brings us to 22,800 years ago, and now this value, 1.91 halved, is our 0.96. So what this means is that we can make an assumption that our woolly mammoth hair is about 22,800 years old, and that is the answer. And that is all. Over and out.